This video is going to cover Trig Notes 5.5. We're going to be dealing with exponential and logarithmic models. In other words, story problems that we can solve by either using an exponential equation or a log equation. The first type of problem that I want to show you is an exponential growth formula. It actually isn't the exponential decay formula too, it's just going to be a little bit different when it's decay. So as we look at this exponential growth formula here, we need to make sure we're aware of what the variables stand for. So I've listed out what the variables stand for over here. Your y value will be whatever your ending population is. Your a value will be what your starting population is, so ending and starting populations. E is just the number 2.7 something, dot dot dot. B is your growth rate, okay? How fast your population is growing, or if it's a decay problem, if you are breaking something down, like maybe a chemical, the B value would be a negative. So it's positive when it's a growth formula, it's negative when it's a decay problem. And then finally, X is going to be your time. Now you may also see the equation written this way, y equals a e to the k t, where k is also standing for your growth rate and t would be your time. So sometimes you may see it written as a e raised to the kt or a e raised to the bx. Again, b and k stand for growth or decay, and x and t stand for time. So it's going to be important that we identify what we know so we can figure out what it is that we don't know and then use that to help us find what our answer is. So these growth and decay problems are usually a two-step problem. So let's read the question first. It says, in a city, the population in 1990 was 2 million. So the population starts out as 2 million people, and 10 years later, in the year 2000, it is 3 million. So that's the first piece of information that I'm going to use. So first, we know that our starting population is 2 million. I'm just going to put it in as a 2 and recognize that when I solve, my answer will be in millions. My ending population, which is y, is 3 million. My k, which is how fast my population is growing, I don't know, or my b, that's what I'm trying to find. And then my t is what is the time it takes to go from 2 million to 3 million. Well, from 1990 to 2000, that's 10 years. So plugging in this information into my formula, I can find b first. That's what I want to know. So y, 3, equals a, 2, e is e, b is b, because I don't know it, and x or t is time. So I guess I kind of use a combination of both of these. We could say this is x or t. So how would I solve this? Well, I have to isolate the e. So I'm going to divide by 2. So 3 over 2 is going to be equal to e raised to the 10b. Now that you have your base here of e and a base of 3/2, this is where you'll write your problem in exponential form. So no, I'm sorry, you don't want to write it in exponential form. It already is in exponential form. You want to apply logs. I was not thinking properly on that problem. You want to apply logs to both sides. And in this case, you want to apply the natural log to both sides. So if we apply the natural log to both sides, our problem would look like that. Now that will allow me to take my exponent and write it as a coefficient. So the natural log of 3/2 equals 10b times the natural log of e. Now remember, we said the natural log of e is 1, so it's not really there. We divide by 10, and we're going to find that b will be equal to 0.0405. We'll round to 4 decimals for our b here. So let's kind of keep that in mind as a rule of thumb. Round to 4 decimals. So if that's our b, that's our growth rate. Now, it's good that we got a positive number because it means that we're growing. If this growth rate was negative, it means our population was decaying or was getting smaller. So now I can actually answer the last part of the problem that says predict what the population will be in 2010. So the second time that I do the problem, my starting population is still 2 million. I want to find the ending population. That's what I'm trying to find. I don't know what that is. My B now, my growth rate, is 0.0405. And my T is from the year 1990 to 2010. That's 20 years. So my time is 20, or I guess that's an X. So plugging it into the equation now, we'd say our Y is what we're trying to find. Our A was 2. Our E is still E. Growth rate 0.0405 times our time of 20. Punching this into the calculator, we're going to end up with, again, when you punch it in the calculator, make sure when you raise it to the E power that you get a set of parentheses around here. You end up with Y being 4.5. Now remember, when I listed it over here as 2 and 3 for our starting and ending populations, that was really in million. So it's 4.5 million people. Okay, so this one says radioactive iodine, a byproduct of creating nuclear energy, has a half-life of 60 days. So let's first talk about that half-life of 60 days. If I start off with 10 grams, 60 days later I'll have half of what I started with. So 60 days later I'd have 5 grams. 60 days after that I'd have 2.5 grams. 60 days after that I'd have 1.25 grams, and I'd keep going on and on. So it takes 60 days for it to go from starting value to half of that. The question says that 20 grams are released into the atmosphere. How long will it take for the radioactive iodine to decay to a level of 1 gram? Okay, so if I think about what I need here, this is going to be an exponential decay problem. I know it's going to be decay because my product is decreasing. So the first time that I do this, I've got to start off with my Y, my A, my B, and my X. So it says right away 60 days is my time. So time is 60. I have 20 grams that are released into the atmosphere, so that's what I start with. I start with 20 grams. And because we're dealing with a half-life problem, if I start with 20, half of that in 60 days would be 10. So I have to actually calculate what the half-life would be. So again, this would have to be half. And then finally, I can find how fast it's decaying, and that's what I'm trying to find is the B. So let's plug that into my formula. 10 equals 20 E raised to the B times 60. One thing I want you to notice when I start to solve this, when I divide by 20, I get half over here. Anytime we're doing a half-life problem, when we start this out and we start to solve for this E, or to isolate the E, this always should result in a half if we're dealing with a half-life problem. Okay? Just the first time that we go through and do this. So now how would you solve this? You would apply natural logs to both sides. So let me just kind of apply natural logs, which will allow me to write this as a coefficient out in the front. So natural log of half equals 60b times the natural log of e. Remember that natural log of e is really a 1, so we'll divide by 60 to get our b. So doing this, natural log of half divided by 60 gives me a negative 0.0116. Again, we'll round it to 4 decimals here. Shouldn't be a surprise that I got a negative because I was decreasing. Okay, so when my growth rate here is negative, that means that it's a decay problem. So that's what you should be looking for. Okay, so we found the decay rate, or the growth rate. In this case, it's a decay rate. Now let's answer the question. How long, so find time, for it to get to 1 gram. So the second time that I do this, putting down my variables again, we just found our growth rate, negative 0.0116. Time, our x, is what we're trying to find. We want to know how long it will take to go down to 1 gram. Well, my starting size was 20. So I started with 20. I want to know how long it will take me to get to 1. Let's plug these into the formula. 1 equals 20 e raised to the negative 0.0116 x. So now this time I'm not going to get, when I divide by 20, I'm not going to get 1/2. Okay? That's only going to be true the first time that I do that when I'm setting up my half-life problem. Now that I know my growth rate, I'm not trying to get half anymore. Okay, so 1 over 20 is equal to e raised to the negative 0.0116x. Apply natural logs to both sides to solve. This would come out as a coefficient in the front. And remember, the natural log of e is 1, so we'll end up dividing by negative 0.0116. And doing that, I end up with 258.3 equals x. And since x is time, we're given a time initially in days, this would be days. So it should take about 258 days to go from 20 grams down to 1 gram. Okay, so for our next problem, we are actually given a formula that's going to help us to solve this. P would be the ending population. 25,000 here would be the starting population. E is E, K is going to be my growth rate, and T is going to be my time. So I start off with a population of 25,000 people. And they're saying that a T of 0 is, the starting year is 1990. And now what they're telling us in 1945, the population is 3,350. Find the K, and they're using K as the growth rate, and use this result to predict what the population will be in the year 2010. So again, let's think about what we're given here. We're using K as our growth rate this time, and T as our time. So we are first given the fact that we start off with the 25,000. Again, and I'm pulling that out of the formula here. And my ending population is going to be 3,350. Now that may not make sense to you, but it will in just a minute here when we think about our time. So if this is what we started with, and our ending population is 3,350, that means we're going backwards in time. So our T is actually going to be negative 45 years, because from 1945 to 1990 is 45 years. But if we're talking about this being year 0, then 45 years before that would be negative 45 years. So our T is going to be 0, and our K is what we're trying to find. So let's plug it into our formula. P, which was, actually they used a P, I wrote it over here as Y. We can think about this really being our Y, if that's helpful. So 3,350 equals 25,000 E raised to the K, which I don't know, times negative 45. So let's isolate this E by dividing by 25,000. When I do that, I get 0.134. So then E raised to the negative 45K. And then I can apply natural logs to both sides and get the natural log of 0.134 equals, write your exponent as a coefficient, negative 45K times the natural log of E. Now the natural log of E is 1, so I don't need that, so we'll get rid of the negative 45 by dividing. So here I'm going to get my K as 0.0447. Now I shouldn't be surprised that it's positive, because if I really think about it like this, my population started here and it grew to here, so the growth rate is positive. We handled this situation where it looks like it would be negative by making the time be negative. So that's our growth rate. I will finish the rest of this problem in the second part.